times. All right, we're live.
Excellent. Thank you, everybody, for tuning in to Reading and Research Night here on Ether Cosmology. For the typical disclaimer I always throw out there on these nights, this is not a presentation night. This is not a put it in a nice package for you to open up and enjoy night. This is us reading, researching live on the spot. And so this, don't expect it to be presentable necessarily. This is for us to give you an insight into what our research process looks like. So with that said, let's go ahead and get into it. So we're going to start with just a quick summary of the geodynamo here. And so I would direct everybody in the Discord to my screen share. And then after we watch this, we're going to watch a quick little 15-second clip of the turbulent motions that are in the outer core. And then I'm going to pass it over to Alan's screen share for about 3 minutes, and then we'll come back and do a bunch of reading. So, at the heart of our planet, the Earth's core is mainly composed of liquid in the outer core and solid in the inner core, iron. Its formation and differentiation is one of the significant events in the early history of our planet. The planetary accretion and radioactive heat is evacuated from the core through thermochemical convection. The solid inner core has appeared at least a few 100 million years ago and is constantly growing as the planet cools. Convection in the outer core is believed to be at the origin of the Earth's magnetic field through a dynamo effect. A fluid motion within a pre-existing magnetic field creates electric currents, which in turn induce a magnetic field that reinforces the pre-existing magnetic field. The central research questions are: how does the geodynamo work? Despite the huge computational difficulties that are involved, can we model this process accurately? From the fast dynamics and geomagnetic jerks occurring over years and less to the longest features such as the geomagnetic reversals occurring once every few 100,000 years. Can we use the geomagnetic signal together with numerical models to probe the structure, history, and dynamics of our planet? How does the outer core couple with its adjacent layers, the inner core and the mantle? Can we forecast the future evolution of the geomagnetic field? The geomagnetic signal. We know that the magnetic field of the Earth has been sustained for at least 3 billion years because of the magnetic signature embedded in minerals present at the surface of the planet. Over more recent epochs, lava flows and lake sediments also provide a way to sample the evolution of the geomagnetic field. Archaeomagnetic artifacts are also used in order to infer the field over the last centuries. The use of the compass marks the start of the historical geomagnetic era. Invaluable data can be gathered from ship logs over the last 4 centuries, starting with the discovery of how to measure the intensity of the Earth's magnetic field, thanks to Gauss in 1888. The observatory era has seen the construction and operation of numerous magnetic observatories over the land surface of the Earth. Since a few decades, magnetic satellites provide a global and continuous coverage of the geomagnetic field evolution. Just one moment, please. I'm going to take a quick drink of water here. Thank you. When measured with proper coverage, the magnetic field at the Earth's surface can be downward continued to the boundary between the liquid core and the mantle, the core-mantle boundary. Highly detailed images of the magnetic field close to the generation region can then be constructed over the observatory and satellite era. The most notable features of such geomagnetic field models are the westward drift of the equatorial magnetic flux patches and the presence of high-altitude flux patches with an oscillatory behavior around an equilibrium position. Our main challenge is to understand the physical reasons and the fluid flows underlying this pattern of surface magnetic evolution. Physical models of the geodynamo can be constructed, and numerical computer simulations are carried out in order to achieve this goal. So here is radial magnetic field at the core mantle boundary in milliteslas between epochs 1590 and 2020 from the GUFM1 Jackson et al. In 2000 and COV-OBS from Gillett and et al. In 2013. This is, their geomagnetic field models.
Because we definitely have the data going back to the 1600s in South America, what was happening with the magnetic field. Right.
There you go. And so just, what does this come from? Well, this comes from this. Boom. That's what's going on inside.
Wow, dude, I've never seen that. They had an animation for it. I know they figured it out. Look at
There
that.
you go. Just like that.
Wow, it was hiding in there the whole time.
Damn.
They were looking for it.
So if mass attracts mass, what's keeping it in the center? Because there is no gravity in the center. It should be flopping around and shit. You know what I mean? It should be. Shouldn't the sun be pulling it to the side or something? And you're like, come on, man.
Cool. Hey, do we have a magnetic field or not? Okay.
Hey, wait a minute, Stone. It sounds like you're trying to introduce actual solar system dynamics.
That big old G. There are consequences to waving that flag, you know?
Yeah, I don't know if you've met my friend. Her name is Selective Application. So we don't really apply the G in this regard. Yeah. So I think you should probably just meet her and see what's up.
Oh.
So yeah, whenever you're ready, Alan, to play the video here, now we're going to learn about the magnetic reversals and the seafloor spreading.
Yep. Here we go. Magnetic seafloor spreading and reversals.
Hi, everyone. Hi, everyone. We're going to talk about the Earth's magnetic field and how the reversals in the Earth's magnetic field revealed that seafloor spreading is happening. The Earth's magnetic field creates lines of invisible force that you can't see, but that your compass...
It's at the highest that the video will play at. You can turn me up though.
Wow.
From your thing on Discord though, if that'll help.
Yeah, I am hearing it just fine.
And the reason your needle points north is that these field lines emerge from the south magnetic pole and wrap around and point toward the north magnetic pole. Now, we know that the Earth's magnetic field has actually reversed, flipped around, so that these arrows would all point the other direction, coming out of the north and pointing into the south pole. And these are called magnetic...
Oh, what's up?
How do we know that?
Stone, did you say something?
No, we're good here.
Okay.
Magnetic reversals. They happen every few million years. The Earth's magnetic field flips back and forth through time. The reason we know this is that lava flows, like this lava flow on Hawaii, when lava flows out of the Earth, it actually, there's little magnetic minerals in the lava, and they line up with the magnetic field at the time and actually preserve, like a tape recorder, the direction of the Earth's magnetic field, whichever way it was pointing, either normal or reversed. So if we go look at a whole series of lava flows, what we'll find if we sample through the lava layers into older and older layers, we'll find some layers that are oriented with the magnetic field, say like today, and other layers, older layers that are reversed, and then still older layers that are like today. So through geologic time, the Earth's magnetic field flips back and forth, and we call these magnetic polarity reversals. Now, the way that this all relates to seafloor spreading can be realized by remembering that lava is pouring out of the Earth at mid-ocean ridges. Okay, so I want you to imagine that we're going to let this ocean basin spread, and we're going to let the Earth's magnetic field flip back and forth as the ocean basin spreads. Remember that when the lava erupts and cools down, it records the direction of the magnetic field at the time, whether it's normal or reversed, backwards or forwards. So we'll start the animation here. We're going to start it at a time when the Earth's magnetic field is like today, what we call normal polarity. And as the seafloor spreads, it's all going to get polarized in the direction of the magnetic field, shown by the blue part of the ocean floor. But now we have a reversal happening, and any new lava that erupts is going to get magnetized in the opposite direction. So you can see the little
I think
compass
they should have
needles
called
here
that zone
flipped,
the
showing us that all
Eratosthenosphere,
this
just to see people mispronounce it.
Eratosthenosphere? I got it.
new
For sure.
seafloor is recording the direction of the Earth's magnetic field at a time when it was reversed. Now we'll let the Earth's polarity flip again. Any new lava that forms is going to record the polarity of the Earth at that time. So what we see on the mid-ocean ridges of the world today is a series of stripes, symmetrical stripes on both sides of the ridges of seafloor rock that's magnetized in the same direction as the magnetic field today, older rock that's reversed, still older rock that's back to normal. This pattern is impossible to explain if seafloor spreading didn't actually happen and the Earth's magnetic field didn't flip back and forth. So it constitutes some of the best
There you
evidence
go.
we have that the seafloor is actually spreading over geologic time.
Well, we must have been evolved from monkeys then, I guess, right? You could nailed it.
Wow.
Yeah, I bet the whole thing's a lie.
No, how...
Let's see what the comments are saying here. Very informative. Thank you. Thank you. Learned a lot. Very nice.
So that was just kind of to give you some context of, you know, where a lot of our assumptions have to come from with the geodynamo theory, and you combine that with seismology readings, and that gives you your P and S wave shadow zones. And so we must have convection currents. If they're there, they got to be in the outer core. But so let's talk a little bit more about that field reversal.
So it for sure happened then, right? That's like...
I mean, well,
real quick,
you saw the
real quick,
evidence.
real quick before we move on. So they're saying that the magnetic field at the time when the lava was created, there's polarization in the structure of the cooled lava that indicates that the field was going in one direction, and then sometime later new lava, etc., and then it's polarized in the opposite direction, and they're equating this to magnetic flips
Yes,
or
sir.
reversals. Okay. Just want to make sure we're
They are
all on the
quite
same...
confident that the lava flow has been quite consistent with their expectations for multiple millions of years, and they are quite confident that the story of the magnetic field must match that of the striping of said lava cooling at said rate, and as such, there must be reversals that have occurred. And during those reversals, there probably was massive extinction of events. And what do you know? We probably have a reversal coming sometime in like 2050 or so. So get ready for a massive extinction event and panic a little bit, just in case you weren't panicking about something else.
Well, hopefully
So
some
stock
labs
up on
will...
extra Aether Hot Pockets.
Yes,
Nice.
yes. Ether Cosmology Hot Pockets coming to a bucket to be shipped to you. Patriot Ether Cosmology Hot Pockets.
Dude, I was just say, is that like my Patriot supply? It's in the bucket of Ether Pockies. Dude, that's what's
Get 'em
up.
now.
Promo
All
code EtherCos. That's what's up. My Patriot Hot Pockets. Ether Pockets. Yeah.
All right, so
All right.
what Stone said, though, at first is like got me thinking. Is like, of course, we had the magnetic data from the 1600s prior to shipbuilding in South Africa in the jungle. Like, that makes perfect sense. But obviously, how much data do you think they do have, and then just spooled it out?
Good question. I would imagine they've got some significant numbers in the north, right? And then everything on the south would just kind of be based off of corrections made later.
Well, so you
Lost to human sacrifice.
I mean, there was a big expedition in the, I want to say the early
Yeah,
1800s.
yeah, right.
They went out with, I can't remember what the name of the device is, but essentially it's a magnometer that can determine multiple vectors and intensity across multiple vectors, and they sent out these royal men from, I want to say it was Britain that did it, sent them around the world and took a bunch of readings. But it was like something that lasted over, I want to say it lasted like a whole century. I don't know. I would have to go pull up the sources.
So you do like a magno survey or something, magneto survey. But that explains why we have so many different maps that have all sorts of different data. We have magnetic flux data, we have magnetic field, we have
Now they use MagSat. They use satellite data. That's what
'Cause
they
even-
claim most of their modeling from.
Right. Even when I was doing tides, though, the magnetic came up, so I have a couple different maps of the versions of it, and then I'm looking at the versions like, why are these so vastly different all the time? Why are there 17 maps of the magnetic field that I have to look at? Like, what? Oh, got it.
Well, yeah, you've got actually real quick. I guess let's look at some pictures of that, because you've got a bunch of different things to consider when you're looking at the magnetic field. Perfect. Here we go. So you have the main field inclination, and then you have the horizontal intensity, and then you would have, so this would be across like one of the horizontal axes.
They have that data rolled back to the 1600s too, though.
Well, obviously they can't have that to a very high level of precision. And then you have the down component. So this is how much is coming down, which as if you look, there's in a lot of cases here. Like here you have, what is this measured in again? It's I believe it's microtesla?
Those are nanotesla.
Nanotesla, thank you. So you have 60,000 nanotesla in the down component up here, and then in the previous picture, horizontal, only 10,000. So in a lot of cases, it actually ends up being a higher intensity with the down component than with the horizontal component.
I'd like to take this moment to point out the obsequiousness of the charts that we're looking at right now, expressed in terms of nanoteslas, when everything on these charts are 5 digits long, as in you could just
Good
make
point.
it 10 to 40 microteslas and not complicate the brain with juggling all these decimal points back and forth. Thanks, guys.
That is a really, truly weird decision. It's a very good point. Like, what?
They did one.
That is one.
There's one. And what's it measured in down there? I can't see.
It looks much more impressive when you have 6
2
decimals.
degrees.
Yeah.
We'll just have. Oh, that's why. Because it's just degrees.
Oh, yeah.
So
Yeah, I
not
don't-
thanks, guys. This part was obvious.
Yeah, I don't even trust scientific data unless it's behind at least 10 decimals.
And a paywall or whatever.
And
And a
paywall.
paywall.
Yeah. If I don't have to resort to pirating it to obtain the information, like I honestly don't even consider it.
So yeah, let's go ahead and read about the polarity reversals then. So studies of geomagnetic polarity reversals have generated some of the biggest and most interesting debates in the paleomagnetic and wider solid Earth geophysics communities over the last 25 years. This is from 2016, 29th of April. Earth's natural magnetic field is generated by complex motion of molten iron alloys in the outer core of the planet, at depths in excess of 2,900 kilometers, and varies on timescales ranging from milliseconds to millions of years. At irregular intervals lasting several 100,000 years on average, one of the Earth's most remarkable phenomena takes place. The Earth's magnetic field reverses, and the north and south magnetic poles switch places relatively quickly. During this short time period between the two polarities, the geomagnetic field changes can be magnetically recorded by sediments and sequences of lava flows. These magnetic data are of value to paleomagnetists in reconstructing past geomagnetic fields, and more specifically in constraining the structure and geometry of the transitional field more accurately. Studies of geomagnetic polarity reversals have generated huge debates in the paleomagnetic and wider solid Earth geophysics communities over the last 25 years. Some of these debates were among the most interesting ones in Earth science over this period. Nevertheless, the topic has received less attention in recent years because of widespread difficulties and controversies concerning data reliability. A recent article published by Reviews of Geophysics by Jean-Pierre Vellet and Alexandre Fournier of Institut de Physique du Globe de Paris or Globe de Paris, provides a mature reflection on the challenges faced in such research, with a critical review of the main reversal features derived from the paleomagnetic records and analyses of some of these features in light of numerical simulations. As well as providing a critical review of past work, this contribution is sure to provide valuable direction for future research on the subject. AGU asked the authors of the article to highlight the important results that have emerged from their research and some of the important questions that remain. Why is this topic timely and important? What recent advances in particular are leading to a new understanding or synthesis? Reversals are one of the most enigmatic characteristic of the Earth's magnetic field, and as so, they generate many questions. How often do reversals occur, and how long do they last? What is the field morphology when it reverses? Does the field weaken or collapse and then recovers with the opposite polarity? What are possible consequences of reversals for the biosphere? When should the next reversal happen? Reversals are relatively rare events if we compare their duration with the length of the polarity intervals. The unique observational evidence for the behavior of the field during a polarity reversal comes from records of the paleomagnetic field. For almost 50 years, paleomagnetists have attempted to gather information by studying sequences of lava flows and sediments which acquired their magnetization during their formation and studied this signal over geological times, or stored this signal over geological times. However, reversals occur over a few thousand years at most, and it is a real challenge to acquire detailed information over this short transitional period between the two polarities. In fact, there is no perfect magnetic recorder. Most sediments are characterized by low temporal resolution, and volcanism is sporadic in nature, with lava flows irregularly distributed in time. Oh, okay.
This is a shady method, therefore.
Wow. At least they've acknowledged as much, I guess. But then why do they even extrapolate anything? It's so ridiculous.
Look
all they
at the
got,
size
Captain.
of the paragraph in which they buried that.
Right.
Yeah, can we get a highlight on that? Nice little spotlight.
Yeah, let's see here. Let's do red, yeah. Or purple seems good.
Well, wait, is there like a gayer option, for instance?
Well, we could go pink,
No.
but I think purple's good for this one.
But it's pretty funny. The farther you get into it, it's like, well, the less and less accurate we have to tell you it is, turns out.
Right. It was thus necessary to decipher the paleomagnetic records that have been gathered around the world by reviewing critically the dominant geomagnetic features. Recent progress in studies of geomagnetic reversals is also due to numerical simulations that have provided new insights into the mechanism of the geodynamo and its reversals. Go ahead and give that a little yellow.
Here comes the models.
Despite being still far from the Earth dynamo, hundreds of polarity reversals have been documented by numerical models. In many cases, the numerical features are similar to paleomagnetic observations, giving us the opportunity to compare and analyze data and simulations together. What an opportunity! That only happens
They
every now
found
and
it
then.
By creating it? Is that what
And if it's wrong when we do this, then nature was probably wrong. The structure of that's just me, ad-libbing, obviously. The structure of geomagnetic polarity reversal remains largely unsolved. The geomagnetic field is maintained by rapid motions of the conductive, iron-rich fluid in the outer core of the Earth. This liquid moves in complex ways as a result of convection within the core. There is now overall agreement that reversals occur without external forcing, and therefore can be seen as an intrinsic property of the Earth's dynamo. Therefore, So the reversals are an intrinsic property of the Earth's dynamo. Therefore, determining the structure and processes associated with geomagnetic reversals is essential for a full understanding of the geodynamo process, or of the geodynamo processes. Typical timescales that characterize polarity reversals constrain the fluid dynamical timescales and hence our knowledge of the Earth's core. Reversals tell us also how the Earth system responds to extreme global changes of the Earth's magnetic field. What are the major unsolved or unresolved questions, and where are there additional data or modeling efforts needed? Where can we get some more? We've got some computers. What should we use them on? The analysis of the database shows that the overall strength of the field anywhere on the Earth may be no more than a tenth of its strength now. Reversals seem to occur in several phases with a precursor and a rebound. We learned also that field geometry during the transition is much more complex, with several poles wandering at the surface of the Earth. I'll go ink there. That's pretty interesting, and thus can be described as a multipolar field. However, it is very difficult to obtain a good description of the field geometry, quadrupolar, octopolar, etc., and describe its time evolution. This requires to obtain many detailed records of the same reversal, the last one being the best candidate, with good geographical coverage including in the southern hemisphere and polar regions. Sedimentary records are only appropriate to reach this goal, but most records collected from deep-sea sediments do not provide adequate resolution to unravel the field morphology constrained by the very rapidly changing nature of the knots. Wow, someone maybe think maybe the data didn't line up with what they wanted? And oh, man, we just don't have the resolution here, guys.
This shady part 2.
That's hilarious. That govern during the transition between the two polarities. Future studies will have to rely on very tiny specimens that require new technologies and on sequences of lava flows that are rare and discontinuous. What a bummer. Another objective is to constrain further the periods preceding and following the polarity reversals in order to better understand the processes leading to their occurrence. Of particular interest is the evolution of field intensity, and specifically the decreasing and recovery phases prior and after each reversal. Detailed data sets would document how we switch from a stable dipolar dynamo to a reversing regime. Apart from promising developments generated by high-resolution records of relative paleointensity in sediments, changes in cosmogenic isotope production, such as beryllium-10, with its long half-life of 1.4 Ma, what is that, million years? Anyone know?
Yeah, I'd go with that.
Okay. Provide in principle another indirect estimate of geomagnetic intensity changes with time. Beryllium-10 production rate is constrained by penetration of cosmic particles inside the magnetosphere and therefore depends on the strength of the magnetic field. Large beryllium-10 production rate peaks are expected during periods of weak geomagnetic field intensities, and therefore a significant beryllium-10 production increase is observed during geomagnetic reversals. Boom.
Didn't they say they modeled it? They found it by modeling it or whatever?
Yeah, but then the beryllium-10 production rates agreed.
I see. Right.
Are you not impressed?
No, I missed that part. You're absolutely right. I'm sorry.
Yo, Toby. So 1 MA is called a mega annum, and that is equivalent to 1 million years.
All right, so we had it. All right. Sweet. Mega annum. So, yeah, beryllium-10 has that nice long half-life of 1.4 mega annum. But then it's constrained by the penetration of the cosmic particles. And so, yeah, you get more cosmic particles, everything goes haywire, and then we can look and be like, well, it must have produced a bunch more during that time period, and thus, boom, field reversals. We can study them. The past 10 years have seen constructive interactions between the observational modeling communities. Reversals produced by numerical dynamos that simulate more Earths-like conditions will continue as computational power increases. Ain't that the truth?
You throw a bigger computer at it, you'll find all kinds of geodynamo models that align.
Yeah, dude, if you focus real hard while you're searching through static noise, it'll look like what you want in the end.
There is no doubt that the convergence of both approaches will substantially improve our understanding of the nature of the geomagnetic reversals. So there you go. And we could look, maybe someday we'll excitedly hop into Earth's magnetic field, EOS 97, from that DOI. So that was that. I'm going to drink some water real quick, and then we're just going to like whiz through this fun little presentation. I didn't want to read the whole paper because it's really long, but just
you're gonna do like a microcosm of this one. Excellent.
Yeah, we're just gonna like fly through just kind of some of the problems that were some things that Ramandeep Gill say are problems of the geodynamo. So first of all, you got the fact that the field structure is not aligned with the rotational axis of the Earth. So right here you have the rotational axis of the Earth, and then this is the polar axis, or the supposed polar axis of the dynamo, the geodynamo. And the permanent magnetization of the core is not proper for what they model. You've got the secular variation.
Okay.
Yeah, go ahead.
Can we go back? Can we just go back just to that spot right there? Because I got that question or two for Mr. Gill. Hey man, whatever happened to laminar resistance? And I mean that in the context of this inner core, this inner thing we've got going on with the iron and the iron and the iron under different pressures, and some of it's solid and some of it's liquid, and yeah, great, but it's still iron. And if the outer 2/3 of the world is spinning on a particular axis, why would the one on the inside be spinning on a different axis? Whatever happened to laminar resistance? Wouldn't it automatically force it to spin on the same axis? I mean, after 1 billion years of doing the same thing, going around in circles. You know what I'm talking about, gang? That this doesn't make any physical sense in terms of a model.
How dare you?
Just thought I'd point that out.
Well, thank you for pointing that out.
So there you go. You have an 11-degree field separation. Boom.
So laminar resistance would be like you got your
Oh,
Earth spinning.
Theta.
You got your Earth
Theta, why
spinning
didn't you
around.
tell me that you had a big theta? Now I understand. No problem, buddy. You go.
What were you saying, Alan?
Let's see, I can't remember. Oh, what did you call it? Laminar
Resistance?
Laminar resistance, right. So you got your Earth rotating around the inner core, and you're saying that around its axis, right? And then you're saying that there
Yeah.
should be, due to laminar flow, that the inner core should automatically align with that, and the field should be generated by that, rotating inner core should match the axial alignment. Is that the verbiage?
Yes, the
that you
alignment would be
use?
magically the same.
Okay, cool. Yeah.
I was thinking
Makes
about, like,
sense.
why would you need it to be the same anyway? Oh, because it geometrically is necessitated. Got it. Right.
Yeah, and that
Is
is
this inner core? Is that farting? Is this a very smelly core or something? What is going on there?
And to be clear, too, that is what they invoke as the cause of the convection currents. They invoke the rotation of the Earth as the cause of the convection currents.
Oh my.
Yeah.
Right.
So they don't even have this
So
thing that lines up
entertaining.
dynamically.
Well,
Because
there's a
if
few
it
different
was,
models. They have a dynamic geodynamo
Right,
model, and
right.
they have a kinematic geodynamo model. Actually, I think there's a few different kinematic geodynamo models, and certain models seem to be used for certain things when it's necessary. None of them are perfect, but they're getting there.
nice. It's an ongoing field of study. I respect that.
ongoing
Where the field doesn't.
ongoing field of
Field is something.
computational power. So the secular variation the magnetic field does not have the same intensity at all places at all times. So we all know that. We were looking at some pictures of that earlier. And then we've got the old field polarity reversal. The field polarity reverses every 250,000 years. It has been 780,000 years until the last reversal. Is another reversal happening soon?
Who worked on that? Hold on.
So there you go. And then here's about the old Curry point. So from statistical mechanics,
Wait a minute. So they're behind schedules on reverses?
just by like
Essentially,
300% or something, or what is it?
It'll
But only
happen.
they're 200
Okay.
over 200%
Okay.
behind. What is that like?
It's like
200
global
something?
Uno. It's like no one's played a reverse cards in a long time, so they're trying to figure it out.
120% behind, something like that.
So going back to the original video we watched where they've got all these predictions based on the metallic polarity alignment of cooled liquid hot magma, right? And then they attribute the other reversals. So they're saying that there's 250 years in between each one of those, but now they're off by 780,000 years, and they're just still rolling with the same thing.
First assertion. Yes, exactly.
Hell yeah, respect.
Well, you heard what they said about the stuff on the ocean floor, right?
Oh yeah, I forgot about that. That as they examine it more closely, the proof of their model hides more, or whatever. Was it like a hide? Is it like a
Shady 1.0.
uncertainty
The
principle?
more money you put in it, the better our evidence looks. It was like.
Yeah.
And let's just really quickly also remind ourselves here. Let me pull something up. That
Okay, while you're doing that, I wanted to review a much earlier point. This thing about the hot core, this hot iron core in there, and there's all this hot iron stuff around it. And then they say, well, yes, because the Earth is slowly cooling. Well, if that's true, wouldn't that have an effect on climate change?
No, that's also simultaneously getting hot because we need it to, Joe.
So do we have to still stop using plastic drink straws because the Earth is cooling?
Well,
So this is also just a quick little reminder of how we know that there's a solid core, because you've got P and S wave shadow zones that show that it's a globe, and they also show that you have this little area where there's a refraction of some kind of the P waves, and this just, obviously this is solid and this is liquid. Boom. Model attained.
Oh, that's got to be it. Yeah.
science.
So back to the paper, or the presentation. So we've got the Curry point. From statistical mechanics, we know that the Curry point temperature of most ferromagnets is around 1,000 Kelvin. And the temperature at the core of the Earth is around 4,200 Kelvin. So, ferromagnets do lose their magnetization at that temperature, but that's not how the dynamo theory works. We've got our convection currents. So,
Anymore, anyway.
So there you go. And by the way, quick little fun fact. This is, I think, around the same or slightly hotter than the surface of the sun in their model. So make of that what you will.
So let's deal with the order of cause and effect just for a sec. You could even go up to the next one if you wanted to for fun. They're saying that we have a polarized Earth, and that's because there's iron and there's iron. Well, where did the original influence come from to polarize the inner core? There had to be one first. It didn't just spontaneously magnetize itself. It happens, like the Curie point is all about magnetizing materials within a field and then dropping their temperature so that everything's aligned and becomes a magnetically structured material. Where's the outer magnetic influence to start this? It's just chicken and egg stuff, guys.
Well,
Nobody talks about it. Where could that be?
You don't know.
Well, technically, don't you just need it doesn't need to be technically a magnetic force. It just needs to be an electrical current, like a high electrical current, which will create that field just by the motion of it. So they could just claim like cosmic rays or the sun or some bullshit.
Yeah, Stone. I think what they say
But it's supposed
is,
to be static in the middle, right? It's not supposed to be moving anywhere. Maybe spinning a little bit or farting unicorn stuff, but
well, there's like
I don't see it.
They say there's like a temperature gradient within the core, right? So when the hotter part is rubbing against the cooler parts, that friction creates the
magnetism.
Yes, we did. We did kind of gloss right over the actual convection currents. Actually, on that note, that is part of it as well. But they literally invoke the rotation of the Earth as the main cause of that. Not the. I mean, it is called convection currents, but it's based around Earth rotation. And then I believe it's supposed to be a static charge from the friction of the convection currents.
Ah, there it is, static charge. That's where they're getting the charge from.
Imagine all this stuff from the Earth that isn't moving, that isn't round, that isn't there, from the axis that isn't there, all from the motion in the sky.
So
wow.
real quick on that generation methodology right there, right? So let's suppose that's happening in this model. Stone, what should the attenuation rate of that field generation look like? Right? Should it get
the attenuation should be immediate because of its temperature. It should go right to zero. The whole thing's above the Curie point on the outside. You don't have any strata to capture a magnetic field. It's just silly, guys.
I didn't know that was a necessary component of it. I thought that it would just, once you had that convection reaction or whatever, it would just permeate out.
As far as I know, that's the only way to magnetize material, is to bring it above Curie in a field and then drop it below Curie. And there you go. It's got the, they're talking about all the organization of the molecules of the strata according to polarization. That's the way you do it. I don't know of any other one. I just saw self-excitation up there, but come on, man. What is self-excitation? Is that planetary masturbation? What is that?
Yeah, that's pretty much exactly what they just said. Yeah.
Magnetosphere.
Just created its own static electrical field and boom, magnetism.
Oh, and then you can still perpetuate infinitely because of that thing we did. You're fine.
It magnetized all over itself.
So here they are talking about the thermal convection. Large amount of molten iron in the outer core is comparable to 6 times the volume of the moon. And the thermal convection, the inner core is hotter than the mantle. The temperature difference results in thermal convection. That just happens to work magically in the direction they need for their magnetic field. And with the rotation of the Earth, blobs of conducting fluid in outer core rise to the mantle. Mantle dissipate energy through thermal radiation. Colder fluid falls down towards the center of the Earth. Boom. Problem solved.
Colder fluid solidifies and sticks to the outer because it's spinning, right? It's more dense. It's colder.
And if it doesn't cool down, it can't get below it can't do the Curie point magnetization alignment either, right? So like, is that the mechanism that they're talking about in there, or am I confused?
You got it. This is hilarity on wheels. Continue.
Okay.
So we've got the differential rotation. Now this is, so the Coriolis, in fact, induced by the rotation of the Earth. Take that with the forces conducting the fluid to follow the helical path. And then between that, you got convection occurs in columns parallel to the rotation axis. These columns drift around the rotation axis in time, result secular variation. Boom. Conducting disk rotates around about its axis with angular velocity omega. Current I runs through a wire looped around the axis. To complete the circuit, the wire is attached to the disk in the axle with sliding contacts S. And we'll actually look at this in a little bit.
Yeah, so they used a disc
Voltage coming from?
to show this. By the way, I just wanted to throw that out. They
Yeah,
used
that's quite
a plain inertial surface instead of a sphere.
There you
They
go.
use a rotating
Boom.
magnet cooling ball.
There you go.
Sounds legit.
Just take the old homopolar disk dynamo and you're close enough. There you go. Screenshot it, everybody. Make your own geodynamo at home. Or your own homopolar disk dynamo. Not quite a geodynamo, but don't worry about that part. And there you go. So yeah, there's a kinematic dynamo model. We're not gonna. It'd be better to actually read the paper for this, I feel like. But present and future reverse flux patches, along with magnetic field hotspot revealed by MagSat in 1980 and Orsted in 1999. Supercomputer simulations are able to very closely model the Earth's magnetic field in 3D. Laboratory dynamo experiments have started to show some progress, but there are limitations. Success in this field awaits advancements in satellite sensitivity, faster supercomputers, large-scale models. So there you go. Thank you. And let's go ahead and just take a quick little peek at this little article here. This is from the University of Maryland Department of Physics. The Lathrop Labs geodynamo is set for overhaul. In a hangar-sized laboratory off Paint Branch Drive, Dan Lathrop gives the signal, and what he often calls simply the experiment awakens. A huge steel sphere with tubes and electrical wires snaking across its surface begins a stately, nearly silent rotation inside a towering cage-like structure. That's the experiment running at visitor speed, however. When only Lathrop, a distinguished scholar teacher and professor in physics, and his graduate students are present to gather data, they crank up its 350 horsepower electric motor to spin 80 times faster until the 3-meter globe encasing 25,000 pounds of liquid sodium blurs out at 4 revolutions per second. For safety reasons, in the 11 years since he first switched the experiment on, no lab guest has ever watched it run that fast. Lathrop hasn't either, actually. You can't see it at full speed, he said. If the experiment sounds pretty singular, that's because there's nothing else like it on the planet. Lathrop, an expert in turbulent flows, envisioned the giant apparatus and several other smaller predecessors as a way to simulate and perhaps even predict changes in the Earth's magnetic field, which originates in its core and helps protect the surface from harmful solar radiation. While the machine has fascinated the geophysics community and generated useful results about planetary magnetic fields, it has never quite fulfilled Lathrop's hopes. So this year, supported by a recently renewed National Science Foundation grant, he and his lab members will undertake a painstaking process to drain the flammable sodium, dismantle the device, upgrade it, and if the plan works, create a better magnetic field of the Earth. Our planet has a geodynamo, a self-generating, self-sustaining magnetic field created by flows in its molten outer core, a layer of mostly iron and nickel, more than 3,000 kilometers beneath our feet. Swirling turbulence in the liquid metal caused by convection and the planet's rotation gives rise to electrical currents and magnetic fields that feed on each other. So far, go ahead. Oh, I thought I heard a mic open.
No, it was an accident. Go ahead.
All right. So far, Lathrop's experiment needs external current to generate a magnetic field. Soon, he hopes that will no longer be necessary.
we need the chicken. We have the egg. We need the chicken, guys. Somebody give me a chicken.
Doctoral students Ruben Rojas and Artur Perevelov in physics, along with Heidi Myers in geology and Sarah Burnett in mathematics, have been researching ways to modify a hidden inner sphere of the device, analogous to the Earth's inner solid core, by adding texture to create swirling helical flows in the highly conductive liquid sodium, generating electrical currents. It's never been tried before, so the results are hard to predict. Huh. Go ahead and give that a little highlight. I try not to be a foolish optimist, but you aren't going to build an experiment like this without a certain amount of optimism that there are interesting things to see, Lathrop said. The biggest potential prize would be an ability to predict the weather of Earth's magnetic field, which is constantly in flux. Geologic evidence suggests the poles have reversed hundreds of times, most recently 780,000 years ago. And indeed, the North Pole has been moving from Canada towards Russia with increasing speed in recent years. During such a flip, much of the planet's surface could have a weaker magnetic shield from solar radiation. For a preview of what that could be like, look at Mars, which lacks a geodynamo. Even now, solar storms do create problems on Earth, damaging satellites and sensitive electronics, said Sarah Gibson, a solar physicist at the National Center for Atmospheric Research in Boulder, Colorado. For instance, if a massive 1859 solar storm that causes aurora as far south as the tropics hit today, it could fry communications and electrical grids worldwide. Dan's work is really important because it's vital to understand the Earth's magnetic field, which is coupling with what's coming from the sun and creating these magnetic impacts, Gibson said. Lathrop doesn't promote his research with disaster scenarios. A pole reversal may not be in the offing at all. It would take more than 1,000 years. But what about scientific curiosity as well as simple prudence concerning a factor that allowed life to arise on Earth? You think you'd want a solid scientific base knowing, well, how does it work and how did it get here, he said. Where is it at now and where is it going? End of article.
Oh my God.
That guy is deep.
So there you go. There's your
Oh, dude, I am 100% certain in my choices so far in life regarding science and
You're not convinced from their geodynamo experiment? They haven't even put
I'm
the
just
middle
waiting
part
for
in
the
yet.
movie.
They
When
don't
does
even-
this movie come out?
They don't even know what's going to happen when they put the metal ball in the middle.
Like, listen, whatever
I
happens,
want to
it's
buy
right.
this guy lunch. I want to sit him down and, just find out what makes him tick.
What happened to you as a child, man? Like, can you tell me the trauma that you may have sustained?
So I'm
How
gonna.
does one qualify to become a dynamoologist?
Oh, well, actually, I just got promoted. So actually now I'm a pseudo geomagnetist. So it just happens like that, I presume.
I will be right back, you guys.
Dude, a
that's entertaining.
geomagnetist, huh?
They've only been able to create a magnetic field in a sphere using salt, molten salt. They have yet to use any form of metallic material, anything metal.
That was sodium, not sodium chloride.
Yeah,
So it
sodium.
was like a melted metal. Just
It was sodium though.
right.
It wasn't
sodium,
iron.
not sodium chloride.
It wasn't iron. It wasn't nickel. Correct?
Sodium's a metal.
Was it iron or nickel?
It was a metal. Just saying, it wasn't salt. That's all.
What does liquid sodium look like anyway?
It wasn't
Tiny.
salt.
An explosive.
Hmm.
When you hit it with oxygen, right?
Have they tried creating a magnetic dynamo with vibranium?
I think they used unobtainium, but it didn't work as well. So they might try
Yeah, I was gonna
vibranium next.
All right, I'm back.
Dude, did anyone else see like how many times like we're gonna look for some evidence? We're gonna make a model. We're gonna use our own model as evidence for the thing we're looking for. What? Wait, what?
So we're gonna read two more things now. We're gonna jump into some Brenner. Start here with.
Dude, I don't know, Toby. You said that these geodynamo papers were kind of boring, but that last one was pretty good.
Well, that was an article.
Oh, yeah, that last one was pretty good.
Yeah, it was pretty interesting. So yeah, this is what do flat earthers believe is on the bottom of the earth. And I like this one because it kind of gets into a lot of the assumptions that they make, that I thought was pretty relevant from what we just were reading.
It's the Magneto turtle, though, right? Everyone knows that. Oh, no, Brad is good.
One of the favorite pastimes of globe believers is to point out the 4 elephants they say flat earthers think the world is resting upon. That's, of course, hilarious nonsense. No flat earther believes such a thing. What globelings in turn seriously do believe is a molten iron mantle with temperatures between 1,000 and 4,000 degrees Celsius, and a solid iron core with 1,000 degrees C hotter than the suggested surface temperature of the sun. Plus, they believe that a churning molten core produces the Earth's magnetic field, conveniently ignoring the fact that metals lose their magnetism above the Curie temperature. In physics and materials science, the Curie temperature, or Curie point, is the temperature at which certain materials lose their permanent magnetic properties, to be replaced by induced magnetism. The Curie temperature is named after Pierre Curie, who showed that magnetism was lost at a critical temperature. For iron, that temperature is 1043 degrees Celsius, and less for most iron alloys. Metal heated above the Curie point can only hold induced magnetism. That is, they are magnetic only in presence of a magnetic field, but cannot produce a magnetic field. So if anything, the core is magnetic because of the presence of a magnetic field, not vice versa. And there dies one of the globelings' own elephants. Pardon me.
Damn, that's exactly what Stone said. Who came first, the magnetic field or the alignment that produces the
Or the
magnetic
elephant.
field? Yeah, exactly.
Next, gigantic globe elephant is the silly notion that a core almost the size of the moon at a temperature higher than the surface of the sun, which supposedly heats us at a distance of 93 million miles, can be so insulated from the surface as to allow ice caps. The composition of the crust, though, does not read like the stock materials of an insulating company. So here we have the Earth's components. You've got iron, oxygen, silicon, magnesium, and other. And he's saying that it reflects mostly heavier elements not blown away by solar wind during the formation of the solar system, or that's what they say. Most common minerals consist of silica, mixed in varying proportions with other elements, such as iron, magnesium, aluminum, calcium, potassium, and what is this guy? No, what is that? Sodium.
Sodium. Yep.
Felsic equals more silica, less iron per magnesium, and less dense. Example of granite. And then mafic is less silica, more iron, less magnesium, and more dense. Gabbro, basalt. And so, yeah, there you go. Why not you try and have your house insulated with the above materials and spend a hot Florida summer in it, or a cold Maine winter? We have supposedly been sitting on that type of insulation for billions of years, and the ice is still here, unaffected by 7,000 degrees Celsius just a couple thousand miles away. How more detached from reality than elephant can it get? I hear volcanism being shouted from the rear seats. Oh well, think of a 30-kilometer thick layer of rock pressing onto a sea of molten iron with 150,000 psi, and imagine that molten material finding an opening in such a layer. What do you think? When do you think the lava will stop pouring out of the opening? Below images of what looks like volcano tips, but they are spoil tips, which every now and then erupt just like volcanoes, as happened in Donetsk, Ukraine in the 1960s. The volcanoes should be connected to an underground pressurized sea of molten material many times larger than the world's oceans, as silly as believing in elephants. Globe geology is based on silliness, like turtles and elephants, and globe defenders don't even know it, because they never research anything. They just repeat stuff, but heap a lot of condensation on people who do their research. Nicolaus Stenonius from 1638 to 1686, whom scholars still consider as one of the founders of modern stratigraphy and modern geology, was not even a geologist. He was a physician and later priest and cardinal. Yet, after a casual walk on the beach where he found encrusted shark teeth, he went home and postulated the still accepted laws of stratigraphy.
Stratigraphy.
Thank you. I was just noticing that. Okay.
That's
The
about
law.
how things stratify.
Yes. Thank you. So you've got the law of superposition. At any time when any given stratum was being formed, all the matter resting upon it was fluid, and therefore, at the time when the lower stratum was being formed, none of the upper strata existed. Then there's the law of original horizontality. Strata either perpendicular to the horizon or inclined to the horizon were at one time parallel to the horizon. And then there's the principle of lateral continuity. Material forming any stratum were continuous over the surface of the earth unless some other solid body stood in the way. And the principle of cross-cutting relationships. If a body or discontinuity cuts across a stratum, it must have formed after that stratum. Every single point here is complete nonsense and not supported by either observation nor experiment, yet it is called science. So here you have sediments and sedimentary rocks from the old geology book. Just try and wrap your mind around the outlandish idea that at one point in time there's only white material suspended in water. It falls out, the water disappears to where? The sediment solidifies. The water comes back, this time carrying only dark brown material. From where? The material settles. The water disappears again, comes back with yet another colored material. From where? And so on. And for how many times in the above image? The next
that explanation makes sense.
Yeah, that's crazy. The next 2 points are too silly to even consider, and the last point is easily disproved by observations which at the same time disprove the first. Here it becomes clear that sedimentation is a highly dynamic, catastrophic, one-time event where the timeline is not bottom up, but lateral in the direction of flow. A. Fine particles on top set, coarse particles on foreset, fine particles on bottom set. All layers of one event are laid down in one horizontal sequence, and therefore a fossil found in the bottom layer downstream can be younger than one found in the top layer upstream. This dynamic reality completely demolishes the accepted chronology of the fossil record, which is based on a static bottom-up sequence. So, this is equivalent to the turtles and the elephants globlings love to make fun of. So there's the old turtle with the earth and the elephant, or the elephant and the earth's on its back. Honestly, that looks pretty fun. I'm into that. Charles Lyell, from 1797 to 1875, a lawyer by profession and hobby geologist, is another still accepted father of geology, and he added yet another turtle to the globe zoo, uniformitarianism, also known as the doctrine of uniformity. It is the assumption that the gradual geological and meteorological processes observed today are the same that operated in the past. This, like so many aspects of a globe philosophy, has become dogma. Catastrophism, the idea that the large-scale catastrophes played an important role in shaping the world, was declared heresy. All theories are rejected which involve the assumption of sudden and violent catastrophes and revolutions of the whole earth and its inhabitants, and it appeared clear that the earlier geologists had not only a scanty acquaintance with existing changes, but were singularly unconscious of the amount of their ignorance. This comes from somebody who has never left his studio, never done serious research, condescending upon field geologists who did nothing but collecting evidence. Evidence that was not to his liking, though, and therefore discarded. Here's a taste from the degree of Lyell's detachment from reality, which nevertheless still forms one of the core aspects of globe science, quote-unquote. Lyell about the findings of hippodamy in England. The geologist may freely speculate on the time when he heard of hippopotami issued from North African rivers such as the Nile and swam northward in summer along the coast of the Mediterranean, or even occasionally visited islands near the shore. Here and there they may have landed to graze or browse, tarrying a while and afterwards continuing their course northward. Others may have swum in a few summer days from rivers in the south of Spain or France to the Somme, Thames, or Severn, making timely retreat to the south before the snow and ice set in. This is not a joke. This is accepted science. The zero science turtles of Stenonius and Lyell are at the feet of yet another elephant, that of Darwinism. Darwin was totally sold to Lyell and incapable or unwilling of standing by his own observations. He who can read Sir take a drink of water. 1 second.
Dude, I think it's just me that realized that they made us look ridiculous with elephants because they knew theirs had to be like more or less ridiculous by comparison. So I just realized that, man.
Yeah.
Some guy found a shark tooth and invented all of modern science or geology and stratification or strategology, whatever it was.
Stratigraphy.
Like what,
Stratigraphy. Thank
what do
you.
you think's down there? Turtles? Well, definitely not a multi-magnetic neodynamo, not making magnetic currents from a Curie point, dude. What do you mean, turtles? Whatever.
He who can read Sir Charles Lyell's grand work on the principles of geology, and yet does not admit how vast have been the past periods of time, may at once close this volume. From his journals, though, written in the fact of direct observations, a totally different picture emerges. The mind at first is irresistibly hurried into belief of some great catastrophe, but thus to destroy animals, both large and small, in southern Patagonia, in Brazil, on the Cordillera of Peru, in North America, up to the Bering Straits, we must shake the entire framework of the globe. Yet, catastrophism stares any field geologist right in the face, but it is not allowed into the books. Such is, quote-unquote, globe science. Darwinism is nothing but the Lyell dogma translated into biology, as is detached from reality and real observations. Scarcely any paleontological discovery is more striking than the fact that the forms of life change almost simultaneously throughout the world, says Darwin, despite Lyell's dogma and his very origin of species. And in his chapter on extinction, Darwin reiterates the puzzlement he experienced when standing in front of a fossil site of a mass extinction when he writes, "The extinction of species has been involved in the most gratuitous mystery." Because according to his theory, the extinction of a whole group of species is generally a slower process than their production, and therefore the extermination of whole families or orders seemed to him wonderfully sudden. Now here he comes to the defining characteristic trait of all modern science. Against better knowledge, because against his own observations, Darwin declares the following: "It is indeed quite futile to look to changes of currents, climate, or other physical conditions as the cause of these great mutations in the forms of life throughout the world under the most different climates." And then, after 300 pages following the promise of revealing the origin of species, the only solution Darwin could offer was blank intervals of vast duration as far as the fossils are concerned occurred. During these long and blank intervals, I suppose that the inhabitants of each region underwent a considerable amount of modification and extinction. Great science indeed. When clueless, just invent dark time, dark matter, and dark energy. There is not a single observation, demonstration, or example in the fossil record of the origin of a single new species, yet it is considered fact. The idea itself is nonsensical because species is defined as an interbreeding island, a group of living organisms consisting of similar individuals capable of exchanging genes or interbreeding. A mutation, which would be considered a new species, would not be able to interbreed any longer with the pool it came from. But how would this first accidental individual of a new species procreate? Bottom line is that all aspects of globe science are wild speculation only and have been so for hundreds of years. Flat Earth does not pretend to know everything, but first and foremost succeeds to unknow nonsense. Logic and physical principles are the guides, not wishful thinking and mathematics. Nobody knows for sure what is under the ground we stand on and above the skies, and it would be good scientific practice to admit that. The wild speculations of accepted geoscience, not supported in the least by experience, experiment, and observation, are certainly not more than turtles and elephants.
Wow.
Yeah, he's so awesome, dude.
Blew my mind every time with like the simplicity of it.
It
Like, how did
sounds
I
like a
not see
song.
turtles? Like,
Right.
I thought toroidals all the way down. He's like, no, he nailed it in the beginning, nailed it in the middle, summed it up at the end in case you were paying attention.
P.S. Following a suggestion by Mike Miller, I add here in the P.S. something in the way of an answer to, so what's on the other side of the flat Earth? The same question goes for what is above. The idea that the atmosphere is fading out to a vacuum of space is irrational and unphysical nonsense. Take the oceans, for instance. You can calculate the water pressure at the surface of the ocean as being 0, P equals P times G times H, for H equals 0 to P equals 0. So does that mean there's a vacuum outside of the oceans? No, of course not. Would there be, the oceans would be gone, despite what is called gravity, which is falsely given the responsibility of holding onto the oceans. The same principle applies to elastic fluids like the atmosphere. Only because the pressure approaches 0 doesn't mean that there is a vacuum above the atmosphere. Like above the oceans, there must be a medium of some sort which keeps the atmosphere and consequently oceans in place, and Earth, whatever shape, is embedded in this medium. The below illustration shows that without a rigid wall, there is no holding on to a gas, and therefore vacuum of space is infantile wishful thinking, which Newton only gave in to so what he could maintain the equally infantile concept of lumps of matter whizzing unimpeded through emptiness. So there you go. That's that one, and then we're going to do one more. So what is the most accurate map of stationary Earth? And actually, how long is this one? Lots of cool pictures.
Been like a 15-pager. A lot of pictures though.
Whoa, yeah, just glad I checked here. Yeah, we can go through it. How long we been going for here?
Let's
Oh,
see.
yeah, we can
Hour
go
and
through it.
13. Yeah.
We're good. Cool. What is the most accurate map of the stationary Earth? Stationary flat Earth. Good place to start talking about maps is a quote from one of the answers here. F. Fredrickson writes, "That means that any flat maps we make of the Earth either will distort the angles between the distant regions or else distort the relative sizes." And that is accepted yet unreflected view of most of the people who have never navigated any length across open waters or studied time zone maps at any depth, people who have never heard of magnetic declination. The globe is a projection, like any other projection, with its own distortions. But these are so cleverly hidden that it takes some time and some experience out in the field to realize just how distorted a globe geometry actually is. Well, not the 2D representations of the globe, as all of them are naturally heavily distorted, but also your actual globe spinning in its inclined stand on your desk is heavily distorted, because not representing actual reality, and that gives the first and the short part of the answer. We have no trustworthy map of Earth, neither in 2D nor in 3D. There are actually two types of maps. A map that gives instructions, a type of map we are not used to reading anymore, though, because they were made for people who actually use them to get places. Your globe is a mixture of both. It pretends to be objective geometry, but you can't use it that way and hope to arrive where you planned to go. You still have to follow instructions, and these instructions are hidden in the magnetic declination. Magnetic declination is the angle between the magnetic north and true north. Declination is positive when the angle is east of true north and negative when it is west. Magnetic declination changes over time and with location. That sounds innocent enough, but when the magnetic field not have why would the magnetic field not have irregularities that you have to adjust for with your compass course? Well, yes, if it would be irregularities within bounds that would be unspectacular and not worth mentioning, but it is not an irregularity. It represents the regularity of a reality that is beyond your wildest dreams. First, we have a look at the so-called North Pole. We see right away that there is nothing irregular to this picture. This is a magnetic quadrupole. Yield lines which arise only if you have two polarities in opposition and can be demonstrated with two magnets under a ferrocell. Judging from that pattern, we should expect two opposing poles, and lo and behold, there are two south poles in opposition positioned on a flat plane. So there and there, I think he's saying. Yeah. Because that can, of course, not be taught, it's called declination and baked into a steering instruction that gets you from A to B, benign in the northern regions, but getting massive in the southern waters. Here you have a diagram with true north and magnetic declination. So much so that below 60 degrees south latitude, it really gets out of control with up to 170 degrees declination. This is the reason why casual private expeditions into these latitudes are not allowed, contrary to what many Qurans want to believe. And all expeditions to Antarctica are controlled and mostly focused on 2 points. The 2 points with minimum declination, one south of Cape Horn and one south from Australia. Here and right around here. With these instructions, you get from A to B, sure enough, but you have no idea what the Earth looks like. You are following steering instructions, just like in good old times where that was all you got. Here on Quora, pilots have taken over the seat of judgment, elevated by the audience to a position of quasi-infallible demigods. Yet how long have pilots been up there, and how long have captains navigated the oceans and kept meticulous log entries about every aspect of their journey? Roughly 10 times as long, so captains it is, and that includes captains and crew of Whitebread, Vendée Globe, and Ocean Volvo races. Between 50 degrees south and 60 degrees south, they race at an average of 18 knots in 40 days around the globe, quote unquote, which makes for almost 10 kilometers more. 10 kilometers?
10,000.
10,000 kilometers more than a globe has at 55 degrees latitude. This is a long-standing item in logbook entries from voyages to southern latitudes, which always refer to more miles and...
How did I miss that? Dude, no way.
Dude, that's crazy, dog. This is quite. Toby, are you familiar with that guy that does the Vendée Globe race that came out on Taboo's channel and like totally blew it up?
I think I saw it, or at least I'm familiar with it.
Yeah, this is like totally corroborating what he's saying about the race and the speeds and the distances.
Yo, you've exceeded the maximum mileage on that circle of latitude, man. can't be done.
Wow, man.
Well, the southern
Just
seas,
right
they
there
just
the
make
whole
you go
time.
backwards a lot.
Yeah, well, they
matter which way you're
magnetic
going.
deck. They magnetic deck you in the face.
Between 50 degrees south and 60 degrees south, they race at an average of 18 knots in 40 days around the globe, quote unquote, which makes for almost 10,000 kilometers more than a globe has at 55 degrees latitude. This is a long-standing item in logbook entries from voyages to southern latitudes, which always refer to more miles encountered than there should be according to globe assumptions. Then there are the endless lamentations among the long, dark, and cold nights in these latitudes, even during summer, which is reported as being very demanding on the crew. I have sailed a lot between 50 degrees north and 65 degrees north, and there are no long, dark nights in summer. And Earth being allegedly symmetric, there should be no long, dark nights in summer, southern latitudes either. Yet there's not a single genuine 24/7 light video from the south. On the other hand, there's not a single faked one from the north, because you don't need to fake it. Scott Amundsen, South Pole Station, a collection of 6 years of manipulated 24/7 time-lapse clips pretending to show 24-hour light in the summer and 24-hour darkness in the winter, so cheaply done that you can watch the timestamps and the shadows jump over 10 hours. Ooh, we might have to go pull this one up. Yeah. Oh, it's not the video. Dang. Well, that's lame. Does he link to it? I don't think so. Oh well. And that gets us to the most important player, causing the greatest problem in this scheme, the sun. And with the sun, the time zones. Would Earth be a globe spinning in front of the sun, the time zones would be naturally falling in place with some political motivated kinks in it, but generally it should follow a 15 degrees per hour rule from one pole to pole. So when we approach the date line from one side and the other side, or in the other, the sun should be in the same position. But the counting a day apart, right? Wrong. You want to paste a flat surface onto a ball, you have to manipulate the center, i.e. what becomes the North Pole region as well as the equator and below, so that now we have only 21 time zones going around the quote-unquote globe from Alaska all around until we stand on the Russian shore just opposite of Alaska again, or better still, calling from St. Lawrence Island belonging to Alaska a friend in Laurentia 200 kilometers dead north belonging to Russia, and do so Sunday noon, we would expect our friend to tell us that it is already Monday noon. But wouldn't we be surprised to hear it is only Monday 9 a.m., where have 3 time zones gone missing? How convenient. Aren't language barriers which make such a phone call unlikely? Wow. That's interesting. So he said, so this is, we've got St. Lawrence Island and then Laurentia. Let's pull this up real quick. Wait, any Google Earth? I think that was the island he was talking about, right? Or no? St. Lawrence Island. Okay. And then Laurentia. Looks a little bit over here.
Yeah. No, that's Scandinavia.
I mean, he's kind of off on his projection,
Down.
it seems like.
Go down.
Gonna search for it.
Keep going down, right?
No one knows where Scandinavia is. Don't feel bad, dude.
I don't know where Scandinavia is. I don't know where Laurentia is. I thought it was in.
Of course you
and it's belonging to Russia. So, but that is up on top of Scandinavia, huh? Okay.
No, it's Eastern Russia. Scandinavia is over next to the UK. Norway, Sweden, Finland.
What you looking for?
Screen. There it is.
There's St. Lawrence Island.
That's it right there.
Well, that was.
You got both in the shot. Move down.
Oh,
Keep
right
going
here.
down. There's Laurentia right there. You got it.
Oh, okay. So I was
Top left.
misunderstanding what he was saying then. Okay.
But it would be good to put the grid on if you have a possibility to do that, the north-south grid, so that you can see that line of longitude.
I don't actually know how to do that. Here we go. Boom. Wow. So they would be pretty dang close, it looks like. But then what does he say here? That they're... ...200 kilometers dead north. Yeah, okay. Wow. That's weird. That's insane. 9 a.m. and noon? So it's noon in Russia and 9 a.m. here. That's crazy. Huh. Well, there's a question for a Glober. What's going on there, my man?
I could be wrong, but I think Witsit may have had something that talks about what you're seeing here with how they split up the time zones and this location being like an anomaly.
Yo,
Sure looks like it.
Toby, if you check the Discord live stream chat, I put 6 images together. That the one that the Russian time zone, how they have it divvied up, is on the 6th image. Yeah, the bottom one on the right shows it the best, probably.
Cool. Yeah, it's that cute little zigzag.
Yeah, look at that, dude.
There it is.
Isn't that cool?
Yeah, and then we got some.
Boom. So that's what he's talking about right there.
Yep.
Nine a.m. and noon. All right, so back to reading here. How convenient aren't language barriers which make such a phone call unlikely? On a larger scale, the sun in Siberia at 140 degrees longitude must be at the same azimuthal position as in Australia at 140 degrees longitude. That is, in the same time zone, which means same noon time. But it's not. It is 2 hours behind. Why? Siberia, Australia. There is no political reason for that. It is the result of distortion by the globe projection, which doesn't fit the sun's path. We have to assume that people in Adelaide call noon when the sun is at the zenith, not 2 hours before that, and the same goes for the people living in Siberia, because they are not idiots either. They call noon when they see it, not 2 hours off. These distortions are securely placed in locations where there is least attention guaranteed. Wherefore, most of the time zone maps have Siberia and Alaska on opposite sides of the page where no one looks and compares. But it is there that the dateline where the cup shuffle is happening. At the equator, we have 26 time zones, with Kiribati counting for negative 14 hours from Greenwich. And that means Antarctica can't at all be what it is shown to be. It's not even one continent. It's also not an ice wall around a disc-shaped Earth resting on elephants and turtles. The magnetic polarities give it away. There must be two massive continents down there with a passage in between, something that modern ships' positioning systems also confirm. The green ship here below is a tanker plowing that is allegedly a 2-kilometer ice cover over rock at 82 degrees south latitude. Hauling what? From where? For whom? Registered and carry body for which is a clandestine Chinese shipping base. Or here, ships busy in what is photoshopped as as mountain range. And then in single file out of there. Or single file out of there. Wow. That does look pretty shady. Huh. The fact that we are not allowed to see even a rough suggestion of the South and neither any detail of the North, despite the fact that the Google Earth brags about being able to check from space, if the laundry is out in a courtyard, should give us pause for thought and reflect over the appalling lack of a real-world map, because a globe very obviously is not a representation of where we live. If you take magnetic declination for what it really is and draw a map accordingly, it would look as natural as the winds on Null School Global Wind Map over the AE projection. Because it looked too natural and convincing, the owner of Null School had to take it offline, and now only those who took screenshots have access to that information. Shout out to bobwins.com. And this is a suggested correction to the AE projection based on old maps that showed what the Bering Strait between Alaska and Russia looks like. This also fits better with sailing records over the Atlantic versus the Pacific, etc. Interesting.
Yeah, they're connected almost. Right on that meridian line.
South America looks really interesting. Wow. Despite a total lack of anything accurate in way of maps, one thing can be ascertained. A sine wave is not how a rocket, a satellite, or a motion traces around the globe. Take the dots from the above and put them on the meridians of an AE projection, or put the traces of several lunar eclipses together and overlay them on a Gleason map. Like the winds, these traces only make sense over a flat surface and are completely ridiculous around a globe. But they have to trace it that way because it is observed on the ground. It just doesn't make any kind of sense once you wrap it around a ball. You are so used to seeing these diagrams that you experience them as a matter of fact, as scientific, when in fact they are complete nonsense. They are nonsensical as projections like these. Although you could argue that the information given is corresponding to observations. But neither the globe nor the Gleason nor any other map so far presented can be the whole picture, and old references to the world, in fact the oldest references to the shape of the world, give a hint. The four corners of the world. It is the ubiquitous and most common phrase used by all peoples throughout the ages, and this certainly does not refer to a globe. If we start with the magnetic phenomena, a phenomenon most everyone agrees manifests the framework of our world as well as our protector, then we need to go full out and study what two polarities actually create, and that is a squarish figure with four corners between the polarities and the magnetic dome above it. Boom. There you go.
Dang.
He took the same ridiculous map choice that I did. He was like, look, the map doesn't matter. He chose the star or whatever. Yeah, that's
It is
called the
crazy
derelict,
looking.
whatever. Yeah, that one. Yeah, Michael Brown. Yeah, that one.
So yeah, here we go for reading night. That was Geomagnetism. Anyone have any thoughts, questions?
No, that was a great session, man. If we got time, I have the video of Jaren going over the distances in the south not being the same scale when it, because you know how it would have to be symmetrical on a globe
Oh yeah, that's pretty
past the
good.
equator.
Let's watch that.
Yeah, let's watch that and then we'll wrap it up because that
Sounds
was
great.
a body bag. All right, let's see here. Give me 1 second. I think it was around 40-ish minutes or so. Yeah. Let's see here.
Yeah, you should be able to. 40 minutes should be good.
Okay.
Pay attention or else you're not going to get it. And you'll be one of these people who just keeps running around saying wrong.
Oh yeah, this is it. Okay, cool. Thank you. All right.
So they've lied to us so much that the scale of maps actually has to adjust for the flat Earth, not for the globe. Again, let me show you. If you're not paying attention, which is very probably the case, wake up. Pay attention. Pay attention or else you're not going to get it. And you'll be one of these people who just keeps running around saying wrong things and not figuring it out. So let's go way up here. Again, here's 20 miles. See how it's getting smaller. Watch this meter as I go down. You're just going to see each distance is getting smaller and smaller and smaller and smaller. 10. Keep going. 10. 10. Identical. It should be here at the equator. Everything flips, but it doesn't. It doesn't do it until we get to the land portions. And then it starts to go the other way. But again, what they've done is they've stretched all this out. So we're going to look at boats here momentarily. We're going to look at planes because, I want to show you this video. We can watch this just for a little bit because this is what got me on this idea of doing this video because I saw somebody sent me this, like, can you please debunk this? I'm like, man, I shouldn't have to be the one debunking this. Let me find it by going to my history.
All right, that's it. The scale did not reset at the old equator.
Yeah, I accidentally muted my stream or muted you on my stream for a second, but just in case anyone didn't catch what happened there, Jaren was using a shipping app with a projection, Mercator projection, and as he was scrolling down from the top, you saw the proper latitude compression occurring, or latitude expansion occurring, essentially, which just means that, going from the center of the globe on their model and coming down, you should see the distance between the latitude lines expand until you get to the maximum distance at the equator. And then as you go south from the equator, you should see them start to come back together. But what happens is it only expands, hits the equator, and then in the application, it stays exactly the same as you go from the equator to the south. Doesn't match what the projection should do. And it just seems like a convenient place for them to have obfuscation. Just like one extra layer of obfuscation they could use to not have to make it perfectly fit the globe. But yeah, anyone else? Any thoughts? Any last questions, concerns, riddles? Am I
Riddles,
alone?
someone give me a riddle right now.
I don't know. How much wood could a woodchuck chuck if a woodchuck could chuck wood?
Uh, a face but no eyes. I tick. I talk. Who am I? Can you surmise?
My boy. All right. Riddles on command. And I have no idea. Somebody answer that.
No idea.
A clock.
Time zone. Damn it.
On point and everything, dude. That's what's up.
Nice. Well, cool. I'm gonna go ahead and close out the stream then. So yeah, just in case anyone doesn't know, next Tuesday is Alan's debate with MC Toon on the topic of general relativity. So don't miss that. But just a rundown with what's going down through the week. Tomorrow night is Flat Earth Fridays. Shane and Alan will both be streaming. I believe I will be there. And then on Sunday, we may or may not do a Bring Your Own Brenner comp on Sunday evening. And then on Tuesday is that debate with Alan and MC Toon. And we will be here on the Discord, on the Ether Cosmology Discord. We will be watching that debate live. And then afterwards, so that debate is at 9 p.m. Eastern, 6 p.m. Pacific. And afterwards, we will be doing a live stream after show here on Ether Cosmology, where we will be going over that. That'll be at around probably, I'm thinking around 11 p.m. It'll be whenever the debate's over and we've had a quick moment to step away. And yeah, after that, possibly on Wednesday, I will be doing a presentation on geomagnetism in the Geodynamo, but that may go back to the following Tuesday. At this point, we will see here. So yeah, thanks for being here, everyone.